Okay, folks. So let's start. Okay. So today we'll study aspects of symmetric key encryption and then one-time pad. Okay. Okay. These are the references. It comes primarily from Berkeley lecture series, and then the book is also there, right? So you can read the book, and also if you are interested, you can read about crypto in more details from this book. This book by Christopher Pear and Pelz. I don't know how to pronounce it. Pelzdl. Pelzdl. Pelzel or something from this book. Right? It's an excellent book. Only if you're interested in knowing theory of encryption in more details. Okay, all right. So these are the topics that we'll cover. Okay, we'll start with introductions, then we'll study symmetric encryption, we'll study IND CPA, and then encryption. This encryption uses XOR function, exclusive OR function, and then we'll study one-time pad, and then we'll conclude. To start, so basically you will come across these two terms. First is cryptography and second is cryptanalysis. Okay, cryptography is traditionally designing algorithms and protocols, such that a message remains confidential. Note that purpose of cryptography is to keep information confidential. So it only works on the first property of the triad, right? So we have studied confidentiality, then we have I is for integrity and A is for authenticity, or sometimes it's also used for availability. Okay, so here we are considering only confidentiality. Then cryptanalysis is essentially techniques to break cryptography. Okay, so so the one technique, for example, we have seen wherein we trick Alice to send encrypted message back, right? Okay, so those kind of tricks comes under cryptanalysis. Okay, our focus is sometimes we'll discuss about cryptanalysis, but mainly about cryptography. Okay. All right. So goal of okay, just a minute. There's some problem on the screen. Hello. Can you please mute your mic, please? Okay, goal of cryptography is to send messages securely over insecure channel, right? That we have studied yesterday. So cryptography in general talks only about confidentiality. Okay, all right. Okay. So something that we'll cover in top today, of course, is just one of these. Okay, one-time pad, but in general, these are the topics that are discussed. We will be covering some of them, actually all of them, but not go into details. Today we'll study one-time pad, then we'll study AES CBC, we'll study MAC for integrity and authentication. So confidentially, again, we will study RSA encryption, then ELG, AML encryption, digital signatures. So I think we'll just stick to RSA, and then of course we'll cover digital signatures. Right? So some of the things that we learn is hash functions, pseudo random number generator, public key exchanges, Diffie-Hellman, and then key management, that's the digital certificates, and password management. Of course, password management will not go into detail now, because we have already covered password in great details. But there are ways to manage password, right? There is a, you can have a system which is a password manager, and how does it work? So we'll not get into those details, because now note that this by itself, all these things by itself is full-fledged course. Take about 30-35 lectures, right, if you get into great details. So we'll restrict ourselves to basic concepts and applications. Okay, and then we'll give you pointers in case you are interested in knowing more about encryption algorithms, or possibly can think of designing or improving existing encryption algorithm. Okay, the terminologies that we use are, very often we'll use this terminology. Some of these we have already covered, like plain text is nothing but original message. Ciphertext is encrypted or transformed message. After encryption, whatever we get is cipher message. Key is secret that we use for transformation. Then encryption is a method of encrypting plain text into ciphertext. Decryption is just reverse of encryption, that Bob receives encrypted message or ciphertext, then Bob wants to know the plain text, then we'll do the reverse function, which is decryption. And cipher is nothing but algorithm for encryption description. Right? This terminology we'll use very often. Okay, so let's start with symmetric key encryption. Okay, in symmetric key encryption, we'll study here one-time pad. We'll start with one-time pad. Okay. Okay. So now note that with encryption, we provide confidentiality. Okay, such that the message cannot be read by anybody. Okay, so Alice is encrypting the message, and message is going over in secret channel. In between, Eve wants to see the message, then she will not, although she can see encrypted message, okay, which she can't make out what it is, right? That's confidentiality. Now there is another word that comes here is symmetric key, right? The one here at the top. Okay, symmetric key. Symmetric key means that Alice and Bob both share the same key. So Alice encrypts a message, and then Bob, using the same key, decrypts a message. Okay. And then this key is known only to Alice and Bob, not known to, in between anybody. Okay, Eve or Trudy or Mallory, anybody doesn't know this key, right? So now the question you may ask is that how does this key is shared between Alice and Bob? Okay, again, key is to be sent over in secret channel. Okay, so we'll try to solve this problem later, but just want to tell you that in defense, like US defense, it was done manually in the beginning, right? I mean, for example, keys to be shared between people in two different countries or two different cities in the same country, then keys were actually manually printed and shared, and and then it goes over very secure communication medium, maybe a truck or aeroplane or something, that only for military use. That they made sure the keys go personally and physically handed over. But now that's not the way to share the keys, right? So, but we'll solve that problem later. But right now, assume that both sender and receiver, that Alice and Bob, have the same key. Okay. Now, the time, how long this key should be valid? That's another question you may ask, right? This is only for one-time use, or it is forever? There's another question we'll try to solve later. Okay. Okay. Now, what is a key here? Key is not something that of a physical matter, right, or material. Like lock and key we use at home, the key is of some metal, iron. It doesn't matter what the metal is, right? I mean, what matters is that what is the code inside the key, right? I mean, how many, what is the pattern of the key, etc. Right? Now here in computer science, everything is bits and bytes. Everything that goes inside computer is nothing but bits and bytes, right? Then we interpret that. Okay, whether in the form of data structures or programming language or assembly language and machine language, etc. These are all interpretations. But a computer can handle only zeros and ones. So everything inside, remember, in computer is zeros and one. and then hardware is there to interpret that, okay, or run that, right? And hardware can only handle zeros and ones. At the same time, so all OS algorithms, software, everything comes in terms of zeros and ones. So the key is also going to be a bit string, okay, which is nothing but a sequence of zeros and ones. Okay, all right. So anything, okay, when you say the key, for example, for us is a fingerprint, right? Okay, say in mobile, in your mobile, you can do locking and unlocking using fingerprints, but fingerprint is what? Ultimately, it goes as is converted into sequence of zeros and ones, right? So remember that key is just sequence of zeros and ones. Everything else, whether image, text, fingerprint, etc., have to be converted into bit string. All right. So now this definition we have already seen. So Alice wants to communicate with Bob. Alice is here. Wants to communicate with Bob. She has a plain text which she wants to send, and then she has a key. Okay, the key, and this key is same as the key with Bob. Okay, and then she uses encryption algorithm, which everyone knows is a known encryption algorithm, and its even source code is available. Okay, and she uses key to encrypt this plain text into ciphertext. Okay, ciphertext is sent over insecure channel. So now when we say word insecure, it means that the content can be seen by anybody. So Eve, Mallory, all 2D, all are sitting in between can see this, but they can't make out anything, right? And then when it reaches Bob, then Bob uses the same key and then uses a decryption algorithm, which is again known to everyone. Okay, and then gets a plain text. Okay, so this is the method. So what are the steps here? First is the key generation. Okay, so key generation has to be there, and then there has to be algorithm for that. So let's assume key gen is algorithm which generates key k. Okay, and then the second algorithm is or second function we can say is the encrypt ENC which is k is a key. Now input to that is message or plain text message, and then k is the key, and then what we get is C, which is ciphertext. Okay, and then there must be algorithm for reversing it. That's a decryption algorithm, right? So we have DEC as algorithm which takes inputs key and then message that has received, because it would have received ciphertext message, and then it converts into M, which is original message. Okay, so these are three functions. First, key generation. Of course, one step we have skipped is that key distribution, which is between Alice and Bob, because we assume that Bob knows the key. Okay, second is encrypt the message with a key using this known encryption algorithm, and when Bob receives it, decrypt it. So these are three steps. Okay. So what are the properties that we want out of this encryption? First is that correctness. Okay, so it means that when we are encrypting, given the key, whatever be M, value of M or message input string, okay, it should result into the same ciphertext. Okay, same ciphertext means corresponds just one ciphertext. And when we reverse it, you should get value of M. Okay. So basically, decrypt correctness is that decrypting ciphertext should result in a message that is originally encrypted. Okay, so this first thing that's required. So decrypt the message that is received. Received message is ENCKM. Okay, and use the key, and what you get is M for all values of key that this algorithm can generate, and all values of M. This relationship, this formula should be fine. Well, encrypt a message given a key, and key can be generated in any way, in a number of ways, right? Given one value of key, take one value of M, and encrypt it, then using decryption algorithm, you should be able to get the message M back, right? So this second is efficiency. Encryption and decryption should be fast enough. Okay, it shouldn't take infinite time, right? Then it's useless, right? It can't be used. Third is security, which essentially is confidentiality. Okay, so in between, if Alice wants to read, Eve wants to read the message and she doesn't have the key, she should not be able to read. That's confidentiality. All right. Okay. Any question? All right. Okay, let's go ahead then. Okay, so what did we say about confidentiality? Because we said that confidentiality provides confidentiality. Confidentiality, our definition, earlier definition that we discussed in last class is an adversary cannot read our message. Now, this definition is not complete by itself, right? It's not very specific. Okay, for example, what if Eve can read first half of the Alice's message, but not the second half? Can we say it's confidential? Or if Eve figures out the Alice message always starts with, say, dear Bob, or anything else, right? So this definition also doesn't account for prior knowledge, right? Because Eve knows that Alice always writes at the end, sincerely Alice. Okay, or it starts with, prior knowledge could also be that she always starts with dear Bob. Okay, so all these things, okay, so there's a possibility of all this, right? Okay, or she may also know something else, that this message is about buying and selling of a stock or something like that, right? Okay, or she may also know that last bit of message is always 0. So these are all prior knowledge, right? Then our definition doesn't cover that what will happen if there is a prior knowledge. Okay, then we come to this method is called INDCPA, which is essentially short form of indistinguishability under chosen plain text attack. Okay, so now we can give little better definition of confidentiality. So ciphertext that is being sent after encryption should not give attacker any additional information about the plain text. Okay, so we may say that Alice has sent a message that's encrypted with algorithm, but it gives some information to Eve that it ends with 0. Okay, some way to know, right, what the message is all about, right? Okay, so ciphertext should not give attacker any additional information about plain text. Okay, so now let's design an experiment to test whether attacker has learned any additional information. Okay, so let's assume that Alice has encrypted and sent either M0 or M1. So Alice has created 2 messages and sent M0 and M1 to Bob. Okay, so Eve knows either M0 or M1 was sent, but doesn't know which. Now Alice has encrypted and sent one of the 2 messages. Okay, and between Eve is reading that, and by reading, okay, because she has got ciphertext, encrypted text, she should not know whether M1 was sent or M0 was sent. Okay, so Eve reads and ciphertext and tries to guess which message was sent. If the probability of correct guess is half, then we say scheme is confidential. Now here we are not assuming any prior knowledge, right? But we can add that prior knowledge also in some sense, right? Even then, if the probability is half, then we can say is absolutely confidential, right? All right. So here, however, here let's restrict our definition to ciphertext. Give the ciphertext that Eve on insecure channel, because Eve is not the intended recipient. So ciphertext that Eve reads in between, okay, gives no additional information about which plain text was sent, whether it's M0 or M1. All right, so let's now move ahead. Okay, now Eve of course can perform chosen plain text attack. It means that now Eve tricks Alice in encrypting a message, okay, and this message is of the choice of Eve. So Eve decides what plain text to send to Alice, and Alice will encrypt it and send it back, right? This is called chosen plain text. We studied that earlier, right? Okay, so now we can change our experiment to include chosen plain text attack. Okay, so now better definition of confidential, we can say even if Eve is able to trick Alice in encrypting the message, okay, using chosen plain text, okay, Eve can still only guess the message Alice sent with probability 1/2. It means that, okay, before M0 and M1 are sent, okay, Eve sends to few messages, maybe n number of messages to Alice, and gets the plain text, encrypted text back, or ciphertext back. Okay. Okay, and now after that, this experiment is done. Okay, whether M0 and M1 is sent by Alice, then even with prior knowledge, Eve should not be able to find out whether M0 and M1 was sent. That is the probability. Eve can still only guess the message with probability 1/2. Okay, so this definition is called IND-CPA. Okay, all right. Any question? All right. Okay, so in general, we can say that, either here, either Alice has one or Eve has one, right? So we normally define win and loss in this game, right? Okay, so now if the probability of guessing is just half, then we can say Eve has one. Otherwise, if probability of guessing is more than half, then we'll say that if the probability of guessing exactly half, we'll say Alice has one. If probability of guessing more than half, then we say Eve has one. Okay, all right. So now let's see this in terms of a diagram. There's a little change here. Okay, so first is that Eve wants to trick Alice, right? So she does chosen plain text attack. Okay, and here M is sent. Eve sends M some message M, and Alice sends encryption of that message back, right? She encrypts this message and sends her this message back. So what she get is ciphertext here. Okay, and Eve can do this thing any number of times. When we say repeat, it means that this experiment can be done, this step can be done any number of times by Eve. So every time Alice will receive a message from M, she will encrypt the message and send it back. So it means that now Eve can have some knowledge. So it doesn't matter, right? she can have some knowledge. Okay, now Eve issues a pair of plain text M0 and M1 to Alice. So now Eve sends two messages, M0 and M1. However, Alice will choose one of them, randomly pick up one of them. Okay, either M0 or M1, and she calls it pick B. B is either M0 or M1, and encrypts that B or one of the two, which she has randomly picked up, and which we call it MB, encrypts it and send it back to Eve. Okay. Of course, Alice doesn't tell Eve which one was encrypted. Okay. All right. Okay. Okay. And Eve may, so now after this, again, you know, Eve, if she wants, she can do the same thing, that she can again send plain text of her choice and get the encryption, encrypted ciphertext back. Okay. So what do we conclude from that? So now we say, if Eve correctly guesses which message Alice has encrypted, whether if you can find out the M0 was encrypted and M1 was encrypted with correctness, right? So correctly guesses, then Eve has won. Otherwise, she loses. Okay. So how does Eve guess whether M0 and M1 was encrypted? That's her choice. I mean, she may have n number of methods. Okay, if she can find this out, then she has won the game. It means that now Alice has lost. Okay, so any particular strategy she can adopt for this. So now in the game, proving insecurity, it means that this whole encryption algorithm is insecure, but if the probability of winning is greater than half. So it means that there must be at least one strategy that can win IND CPA game with probability greater than 1/2. Okay, because 1/2 is probability of winning by random guessing. Okay, so if you can do better than random, then ciphertext has leaked information and Eve is able to. It means that, you know, whatever prior attempts has been done. Okay, because you know the plain text which Eve will send to trick Alice and get the message back. If she has learned something from that, means that the encryption algorithm is not right. Okay. Okay. So if you can do better than random, then ciphertext has leaked some information, and Eve is able to learn it and use it again to her advantage. And proving security is that for all strategies that are possible, the probability of winning IND CPA game is at most half. All right. Any question? Are you able to understand it?
Yes, sir.
Okay. All right. All right. Now let's. Now, how about the length of message that is being sent? Okay, cipher. Okay, all right. So we'll discuss about this. Now, should cryptographic scheme be allowed to leak the length of the message? Yes. Okay, because otherwise we'll have to fix the length of the encrypted message, and for that we will have to fix the length of original message. Okay, and that is not very practical thing, right? Because if you fix something like 128 bits, then we cannot go more than 128. Your message will be of 120 bits. And let's assume the length of ciphertext is 1 GB long, then it's not very efficient, because a smaller message like yes will also require 1 GB. Okay, so it's not practical. So all right, so So this algorithm should be able to disclose what is the length of the message. It means the length of message can go in a plain text also. However, in our game, okay, in DCPA game, we assume right now M0 and M1 must be of the same length. So in order to break this INDCPA, Eve must learn something other than the message length. Okay, message length is of not any, it's not really importance, right? Even otherwise, if length is published, Eve, Eve should not be able to guess, find out anything more than original message. Okay. Second thing that we need to consider is the attacker's runtime. So in practice, some schemes, encryption schemes may not be totally secure or confidential, because because if somebody does, the number of attacks that are possible could be very, very large, and somebody does all that, then encryption scheme may be breakable. Okay, so some schemes are theoretically vulnerable, like the game that we have seen there, where the probability goes above 1.5, 1/2, then we can say is insecure. But in practice, it could be very different, right? Since, for example, attacker takes say 100 years to break, not a million years. Let's say attacker takes 100 years to break, then the probability is that attacker won't attempt it, right? So then we can say that, sir, even if the probability of breaking is greater than half, then scheme could still be confidential. Okay, so Eve is, so now here in game we can say that Eve is limited to practical runtime, not the theoretically it could be anything, right? So one limit we can say that Eve is limited to polynomial runtime algorithms, not exponential runtime algorithms. Okay, so for example, sometimes it's possible for Eve to win with probability of 1/2 plus 1/2 raised power of 128. So now note that this is very small number. 1/2 raised power 120 is very, very small number. So this probability is close to half. Okay, all right. So Eve's advantage is so small that she cannot use it for any practical attacks. Okay, so in general we can say that scheme is secure even if Eve can win with probability greater than half, 1/2 plus epsilon, where epsilon is negligible. Okay, the actual mathematical definition of negligible is out of scope, right? Okay, so it's so this could be very small advantage, like 1/128 is very negligible advantage. Okay, while we can say if the advantage is of the order of say 2/3, then is non-negligible advantage, right? So all right. Okay, so conclusion from this is that if so scheme is secure, this IND-CPA game, the encryption scheme is secure even if Eve wins with probability which is very close to 1/2, because the advantage that Eve has very small. Okay, any question? All right, so I will suggest you to read it from the book, because a lot of, like, for example, how this number 1/128, 1/2 raised power 120 has come. There is example in the book, so you can follow that up. Okay, so this function, right? XOR function. We will use this function in encryption. Okay, so like, I mean, this function XOR function, yes, and we know that if both inputs of this function are different, then output is 1, and both inputs are the same, then output is 0, right? So this reason is called exclusive OR. When there's exclusive, means 0 and both inputs are different, then output is 1, right? So 0 0 exclusive OR becomes 0, and when they are different, like 0 1 and 1 0, then becomes 1. Okay, so what are the other properties of this? The other useful properties of XOR is that, okay, when you take one input X and you exclusive OR it with 0, then output is X, right? So for example, take two values of X, 0 and 1. So when it's 0, both values are same, the output is 0. Oh, just a minute, yeah. So which is same as X. And then when X is 1, then both bits are exclusive with 0 is 1, so output is 1, right? So it's same as X. Similarly, X exclusive OR with X is 0, and then we have these two properties, right? X exclusive OR Y is same as Y exclusive OR with X, and then other property when X exclusive with Y and the total exclusive of Z is same as X exclusive OR with exclusive OR of Y and Z, right? And so on. And last one is also really important. X exclusive OR Y exclusive OR with X is equal to Y. Now this one we will use. Okay. So basically, if you receive X exclusive OR Y, and you know the value of X, which can be key, for example, then you can retrieve from that value of Y. Okay. All right. So, and then this algebra can also be applied on exclusive OR. Okay, so we can given this thing Y exclusive OR 1 is equal to 0, we can solve it for Y. Okay, and then we can also do, for example, given this one Y exclusive OR 1, okay, which comes from the previous one here, and then we can exclusive OR with 1, which then becomes 0 exclusive OR 1, right? So we can apply algebraic properties also. Okay. Okay, now another, how much time we have? We have about 5-6 minutes. We'll try to cover one time pad. Okay, it's called one time pad. Okay, so one time is important here, right? Like one, we have, we can also call it OTP, but OTP, for example, on mobile you receive is called one time password, right? It means that that password is valid only for one time. Similarly, here one time has some meaning. Okay. Now one time pad is simple. Okay, and idealized encryption scheme. It works well. Okay. And it's just there to illustrate some important concept, although it's not practical in the real world. But in the past, there have been many, the one-time pad have been used in many situations. Okay, so let's look at one-time pad. First thing is key generation. So Alice generates key. Okay, so key is a randomly chosen bit string. So this is the key here. This is the digits that you see here, 0 1 1 0 0 0. These are randomly chosen, because at each position you can choose 0 or 1, right? So there must be some random number generator or something, right? So this key is generated, which is randomly chosen bit string. Okay, now this key is available also to Bob. Okay, how? That we'll discuss little later. Okay, but assume that Alice generates this key using some function and then gives it, maybe manually, personally travels and gives this key to Bob. But Bob has this key. Okay, now this is a message here. Okay, that Alice wants to send. Now, so this message is, of course, will be converted into zeros and ones, and this is a bit string corresponding to M 10011100100. Okay, now we have to get from this ciphertext. Okay, so we exclusive OR it. Okay, so each bit of K is exclusive OR with each bit of M. Sorry, corresponding bit of M. So first bit is exclusive OR 1, second bit is second bit of M, third bit of K is exclusive OR with third bit of M, and so on, and we get this ciphertext. Okay. Now this ciphertext is sent to Bob over insecure channel. Okay. Now Bob receives this ciphertext message, which is here, which is C, and Bob also has a key. And note that this key is same as the key which Alice has generated, right? This key. Okay, this key, same as that, right? Okay. Now Bob can get the message back, the message which Alice has sent by simply excluding ORing these two bits. So this is the message that was sent by Alice. You can check it 1001110, etc. Right? So you can see that same as this message, this one here. Okay. And now what property you have used here? You have used this property, right? The last property here. What is the key here? Key is the X. Okay. So initially message was Y, which Alice wants to send, XORed with key. And when Bob receives it, because this was sent by Alice to Bob, when Bob receives it, then Bob will exclusive OR with key and get the original message Y. Okay. So here it is. All right. Okay. So what we need here, we need key generation. So this is randomly generated n-bit key, and we have we can assume that there is a generator. Okay. Now note here, when we use a one-time pad, it means that we generate new key for every message. Every time Alice sends a message to Bob, she will generate a new key, and then key will be given to Bob, and then message will be communicated. This key cannot be used 2 times. Why? Anyone? Can you think of why key cannot be used multiple times? Okay. All right. So these functions we know by now, right? So key generation, key is generated. So Alice will do key encryption using this one, K, and encryption of message M with K. And this is a ciphertext that will be sent to Bob, and Bob will, okay. All right. So here you note that ciphertext is, so this we achieve, of course, by bit XORing. Okay. All right. So now this decryption is exactly opposite. So Bob receives ciphertext, uses key K that he knows, and then gets this one, right? K exclusive OR C, and then this produces M. Okay. So this is correct, because we know that simple, by decryption of this one, we get message M back. Okay, so encryption is K exclusive OR M, decryption of K, and then message that received is K exclusive OR M, and if you just solve this, you'll get M back. Okay, so nothing unusual here. So, but what we want is that ciphertext should not give attacker any additional information about the plain text. Okay, so Eve should not know whether M0 or M1 was sent in our experiment, or she doesn't know anything apart from that. Okay, all right, so this we know. Okay, so now we can say this is also confidential because it's only K that's important, and we'll see that that value of K she cannot find out. Eve in between cannot find a value of K. Okay, so for example, there are two attempts. Alice sends encrypted message, which was, and the original message was M0, and then use key K. So this message she sends. So ciphertext is K exclusive of M0. Therefore, K is equal to C exclusive of M0. Okay. Now, second possibility, when Alice encrypts message M1 with key K, okay, and then ciphertext is C is equal to K exclusive of M1. Therefore, K is equal to C exclusive of M1. Okay, so K is chosen randomly. So both possibilities are equally possible. Okay, hence Eve learned no new information and the scheme is perfectly secure. Okay, now okay, just go through it. You'll understand what basically I mean by, if Alice encrypts with randomly chosen key M0 and 1, then it does not give any additional information to Eve. Okay, now let's use the same OTP, okay, twice. Okay, it means the key is used, same key is used 2 times. Okay, now M0 and M1 both are sent by Alice and she uses the same key. Okay, so now when M0 is sent, she uses the key and gets K exclusive or M0, and when she sends M1, okay, and uses same key, she gets K exclusive or M1. So earlier she gets K exclusive or M0, then M1. So now what will happen? Eve will see 2 ciphertexts over insecure channel. First is this one and second is the other one. Okay, and what she can do is that she can exclusive or these 2, okay, and then get this value M0 exclusive or M1. Okay, does she know anything about? Yeah, she has now partial information, and from this exclusive or function, what the output she gets, she can also make out certain things. She can make out what bits in M0 and M1 are the same, what bits in M0 and M1 are different. Okay, all right, okay, now she can use this to her advantage, okay, to guess a value of M0 or M1. Okay, and if she is able to guess 1, and then since she has received M0 exclusive or M1, if she could guess 1, then she can find out other very easily, right? So one-time pads are not secure if key is reused. So now Bob and Alice have to use different keys for every message. Okay, and this is not very practical thing. Okay, because it will require a lot of time in key generation, and because we will see randomness is not free, right? It requires time. Okay, and effort. Okay, second is key distribution. So every time Alice wants to send a message to Bob, she has to send the key first. Right, and it's possible if they sit close to each other and she can go personally and do that, but if she sends the key over insecure channel, when Bob and even Alice and Trudy and Mallory are sitting close by, then it may not be a very practical situation, right? Okay, all right. So one solution is that send the keys in advance, and there must be some secure channel in the beginning. Over this, number of keys can be sent. Number of keys would be same as number of times Alice wants to communicate with Bob. Okay, so this could be one solution, but not very practical. All right. So now if that is done, then of course this communication is possible, otherwise not. All right. Okay, so that's all for today. We have looked at one aspect of, one aspect of encryption, which requires both sender and receiver to have same set of keys. Okay, all right. And then we have looked at one time pad, and we have, and before that we have also, okay, sorry, we have looked at IND-CPS security mechanism, and then based on that we have discussed how one pad works, one time pad works. Okay, and we have seen one time pad works only when the key is not repeated. Otherwise, Eve can have additional information which he can use it for her advantage in breaking the system. All right. Any question? Sorry, I have taken a little extra time today. So we have studied symmetric key encryption, we have studied IND-CPS security, and then we have studied one time pad. Okay, all right. See you on Monday then.